we're going to start today by looking at that flow chart that I just passed out. We're going to fill in a couple of things there, and then we'll come back to it after we work through the rest of today's lesson. So we've had a lot of properties of some figures so far, and we're going to have a lot more properties today. So I have this flow chart for you so that we can kind of organize all of this information in one place, and ideally that will help you have kind of a study sheet that way that everything will be in one place together. So we're going to start at the top where it says quadrilaterals. So at the very top it says quadrilateral, and under there there's just one thing that we want to say about quadrilaterals. What does it mean for something to be a quadrilateral?
4 sides.
4 sides. And that's it. That's all we're really going to say about quadrilaterals. They don't necessarily have any special characteristics. They just have 4 sides. Then that breaks down, and we're going to look at the side that says parallelogram. Because we've talked about parallelograms, and we want to fill in some information that we know about parallelograms. The first thing for number 1, I want to be the definition of parallelogram. So what is the definition of parallelogram?
Both sides parallel, both sets of sides.
The opposite sides are parallel. I'm going to put a star by that one because that's the definition. The definitions are important on the test. If I ask you to define something, you should only say what is true by definition, not any other facts that we might know about it. We know lots of facts about parallelograms, but the definition of it is that opposite sides are parallel. But we do need to know what all those other facts are. So there are 7 entries here. So our first one is our definition. What is something else that we know about parallelograms?
Opposite sides are congruent.
Opposite sides are congruent, and I also heard opposite angles are congruent. What's something else that we know about parallelograms?
Their diagonals bisect each other.
Diagonals bisect each other. Okay, that's all the properties that we were given about parallelograms in our first section where we talked about what parallelograms are. But then when we moved over to ways to prove that we have a parallelogram, we had a list of 5 different ways we could prove we had a parallelogram. These were 4 of the ways, and then there was one more way we could prove that we had a parallelogram. And what was that?
Opposite sides. One side is congruent and parallel.
One set of opposite sides, congruent and parallel. Okay, the last 2 are things that we haven't necessarily discussed, but we have actually seen whether or not you realized it in problems. You were using some of these properties. And we'll have number 6 be that a diagonal cuts a parallelogram into 2 congruent triangles. So we actually use that in some of our proofs where we drew in a diagonal and said that cut it into 2 congruent triangles, and then we got some CPCTCs and stuff like that. So we never actually stated this, but it is something that will happen in there, that a diagonal is going to cut it into 2 congruent triangles. The other thing that we're going to say here that happens in a parallelogram is consecutive angles, which means not the ones across from each other. We already know the ones across from each other are the opposite ones are congruent, but consecutive would be 2 angles right next to each other. What do we know about 2 angles right next to each other in a parallelogram?
They are
Supplementary. 2 angles right next to each other in a parallelogram will be supplementary to each other. So we used that fact a little bit back in section 1 when we were solving for some angles in a parallelogram. And the reason is because they would be same side interior angles. And same side interior angles are supplementary. Okay? So that fills out what we know so far about parallelograms. Today we're going to learn about some special parallelograms. And then after we go through our lesson, we'll come back and fill in some more stuff on this flowchart. But we'll go ahead and go over to our notes now. So today we're going to learn about some special parallelograms. Our first type of a special parallelogram is a rectangle. A rectangle is defined as a quadrilateral, 4 sides with 4 right angles. So a parallelogram, or a rectangle, is a parallelogram then, because lots of different reasons. We could say opposite angles are congruent. They're both 90. We could say consecutive angles are supplementary. A 90 and a 90 makes a 180. Because we have so many lines here that are perpendicular, that gives us parallels, which would give us a parallelogram. Opposite sides are parallel here, so we have a parallelogram. So there's lots of different ways why we could say a rectangle is a parallelogram. Our next one is called a rhombus. And a rhombus has 4 congruent sides. A rhombus is a parallelogram also. Why? Opposite sides are congruent. Really all 4 are congruent, but at least the opposites are congruent, so it's a parallelogram. But it's a special parallelogram because all 4 sides are congruent. Question?
What do we fill in for like the blanks?
For the Y's?
Yeah.
Well, I said for a rectangle, there are lots of different reasons that we could apply there by saying that either opposite angles are congruent.
Yeah. So
Oh, on your flow chart? We're not on the flow chart yet. For a square is defined as being a quadrilateral with 4 right angles and 4 congruent sides. So that means a square is a rectangle because it has 4 right angles. A square is a rhombus because it has 4 congruent sides. And it's a parallelogram because rectangles and rhombuses are parallelograms. So a square is a very, very, very special figure because it's lots of things. So there are lots of special characteristics that will be true about a square. Because anything that's true about a parallelogram will have to be true about a square since it's a parallelogram. Anything that's true about a rectangle or a rhombus will also be true about a square. So a square has a lot of special characteristics to it. Some of these characteristics are given here as theorems. It says in Theorem 12, the diagonals of a rectangle are congruent. So that would mean that AC in my drawing would be equal to BD. This is not true in general for a parallelogram because once we take that rectangle and we start to tip it, instead of having it stand straight up, then one of those diagonals will be shrinking and the other diagonal will be growing. So the 2 diagonals are congruent only specifically in a rectangle. It would also work for a square because a square is a rectangle. Theorem 513 says the diagonals of a rhombus are perpendicular. So I have a rhombus, it says the diagonals should intersect at right angles. And we can see that's not necessarily true for any general parallelogram. It's not true in my drawing of a rectangle up there. We can see that in those angles in the middle, we definitely have some bigger angles and smaller angles. But in a rhombus, the diagonals will intersect at right angles. And then Theorem 514 still talks about a rhombus and says a diagonal will bisect the angles that it goes through. And since opposite angles of a parallelogram are congruent, really all 4 of those then are actually the same. And for the other diagonal, again, we will get 4 more angles that are the same, but not necessarily the same as the other ones. Questions? Yep. All right, so now we're going to go back to our flow chart and fill in some more information here about our new figures. So under parallelogram, it branches out to say rhombus and rectangle. Under rhombus, the first thing we want to say is the definition of rhombus. And we'll put a star by that because definitions are really important. And what is the definition of rhombus? Four sides congruent. Then we just had a couple of theorems about a rhombus. And what did they tell us? Diagonals bisect angles. And what was the other theorem that we had? The diagonals are perpendicular. Now for the last blank here, we didn't have any more theorems about a rhombus, but because a rhombus is a parallelogram, that means that everything that's true about a parallelogram should be true about a rhombus as well. So we're going to say all parallelogram rules apply as well. Anything that's true about a parallelogram should also be true about a rhombus. So we're going to state that as well, that those 7 things we had written down under parallelogram are also all applicable to a rhombus. Under rectangle, we want to list out 3 things here. The first one should be our definition. What is our definition of rectangle?
4 right angles.
4 right angles. This is important that I want to make sure that you say that it is 4 right angles, not just 4 congruent angles. They are in fact all the same size, but more specifically than just being the same size, they are all right angles. So on the test, if I ask you to define rectangle, you want to make sure that you say that it is 4 right angles. What did our theorem say that happens special in a rectangle? Diagonals are congruent. And then for our third and final blank under rectangle here, we're going to say all parallelogram rules. Because if it applies to a parallelogram, it also applies to a rectangle. Okay, a few of that just walked right in. You're just want to go grab somebody else's because there's a lot of other stuff from before to fill in here too. We're going to go ahead and go back to our notes then. And we have a few more theorems, but these ones are not directly about our special parallelograms, our rectangles, rhombuses, and squares. But there is a reason why they're in this section, and I'll show you that. So theorem 15 says the midpoint of the hypotenuse of a right triangle. So I need a right triangle, and I need the midpoint of that hypotenuse. So the midpoint of the hypotenuse would mean that it's the same distance from the 2 ends there. This theorem tells us it is equidistant, or the same distance from all 3 vertices. So we can see that it's the same distance from 2 of the vertices because that's what it means to be a midpoint. But this theorem tells us if I connect it to the other vertex that that's actually the same also. That all 3 of those distances are actually exactly the same. The reason why this is in this section is if I wanted to prove this, what I would need to do is kind of copy that figure over, which makes this into a what? A rectangle. And in a rectangle, we know that 2 diagonals are the same size, and we know that diagonals of any parallelogram bisect each other. So that really then I could put in this other one, and it would be the same size, and all 4 pieces there would be the same size. So that's why this is in this section. If we wanted to prove it, we would need to use rectangle properties. Next one says if an angle of a parallelogram is a right angle, so we know that we have a parallelogram, and we know we have a right angle. Theorem 516 says that's enough to call it a rectangle. That we don't actually have to find all 4 are the same. It's sufficient to just say that it's a parallelogram with a right angle. Yeah.
Are we just trying to prove rectangles and
You'll have some problems. There will be 2 proofs in the assignment that ask you to prove that a parallelogram is a special figure like a rectangle or a rhombus. Theorem 517 then says, if we have a parallelogram, and I know two consecutive sides, so not opposite sides, but two sides that are right next to each other, are the same size, that's enough to say it's a rhombus. So you don't actually have to show all four are the same size, just showing that two next to each other are the same size is enough to say it's a rhombus, as long as we also know it's a parallelogram. Okay? So these are kind of shortcuts to being able to prove something is a rectangle or a rhombus. That we don't have to satisfy the full definition, we can just satisfy the shortened definition. Okay? Questions? All right, this was something that was passed out back at the beginning of the chapter. Remember, it kind of came out to you in 3 separate pieces, but this was a sheet that was all by itself. It's just another visual aid along with that flow chart to help you see the relationship and the characteristics of parallelogram, rectangle, rhombus, and square. That the parallelogram is kind of the big general thing, and then inside of there we have rectangles and rhombuses as being special types of parallelograms, and when we put those together, it creates a square. Okay, so just another visual aid to help you organize mentally these characteristics of our different figures. We're going to look at some examples. Alright, so on this, we're going to go ahead and trust our eyes, which I know is a dangerous thing to do, but we're just going to kind of look at the pictures, and by judging just what they look like, we're going to decide which ones look like they fit into these different categories. So which ones in here, and we'll just go numerically on through, starting at number 1, which ones look like they are parallelograms?
1, 2, 4.
Okay, now I'm just starting to hear us counting. So, 1, 2, 4, 5. I'm good with that. What about 6? No. Okay. 7.
8, 9, 10, 16, 12.
Okay. So the 3 that you skipped then, you skipped number 3. Number 3 is something that's actually called a kite. We're not going to study it and its properties in depth, but it actually looks like a kite. And that is its geometric name as well. Number 6 is a special kind of figure that we will talk about tomorrow. Number 11 is not special in any way. It's just a 4-sided figure, but it is not a parallelogram. Rectangles. Which ones are rectangles? Again, going numerically.
2, 4, 8, 9, 10.
Okay, so what characteristic do we need for it to be a rectangle?
4 right angles.
4 right angles. So number 2 is one that a lot of students will skip over because we look at number 2 and we want to call it a what?
Square.
A square. But a square indeed has 4 right angles, so it is a rectangle. It's not an either or, it's actually both. So we need to make sure that we include anything that has 4 right angles within the category of being a rectangle. So which ones look like, and now there's a couple of kind of close judgment calls in here, which ones look like they might be a rhombus?
1,
1 is kind of an iffy thing. I think if we actually measured out, it's not quite, but 1's kind of an iffy one.
5,
2, 5, 7, I don't think is.
No.
12,
9.
9 and 12, I think 12 is. 12 again is kind of iffy.
12 doesn't.
A square.
2,
9.
and
2 and 9.
4.
How could I know that something was a square just by looking at the list we have created so far and not looking at the pictures at all?
Whatever's in both of them.
The overlap between a rectangle and a rhombus, because that's what a square is. It's a rhombus and a rectangle. So we'd want to find the overlap of those two groups, which is 2 and 9. So the next one says rectangle and rhombus. That's really just a way of saying square, because that's what a rectangle and a rhombus is a square. So that again would be 2 and 9. Which ones are rectangles but not squares? They are just exclusively a rectangle.
10,
4, 8, and 10. The ones under rectangle except for the overlap of 2 and 9. And which ones are a rhombus but not a square? 5 and 12. The ones under rhombus that are not also listed under square. 1 is kind of iffy. I think if we measure it, it's actually not. It's hard to tell in the picture from the copy here, but. All right, we have one more set of problems that uses that midpoint theorem that we talked about. In this picture, we are told that M is the midpoint of KP and that the full triangle KAP is a right triangle. So, if MP is 6.5, how long is MA? 6.5. We had a theorem that said if it's a right triangle in the midpoint of the hypotenuse, it is the same distance to all 3 vertices. So if it's 6.5 to P, it's 6.5 to K, it's 6.5 to A. Okay, all 3 of those are the same. If MA is T, how long is KP?
2T.
2T. So if the little inside one is measured as T, KP has 2 of those, so it would be 2T.
Yeah. I thought it was a D. Where is it?
If angle K is 40, we are asked how big is angle KAM?
40.
Why?
Isosceles triangle theorem.
We have a little isosceles triangle right here because we have 2 sides that are marked as the same.
Mr. Perfect.
So that means 2 angles will be the same as well, and that one will be 40. What about if I was asked how big angle MAP is? How big is that?
No.
It is 60.
50.
50.
Why is it 50?
Because it being so right.
Because the corner together makes a right angle. So if the lower part is 40, together they have to be 90, the upper part must be 50. How big is angle P up in the top corner?
That would be a big old 50.
50, because once again, we get another isosceles triangle up there.
Nice going, man.
Okay. Your homework problems tonight are from section 5.4.